It's my great pleasure to introduce Benoît Perthame from Sorbonne University to give the second Distinguished Visitor Lecture series. So Benoît has made fundamental contributions to the study of nonlinear PDEs and their applications in mathematical biology. So for his contributions, he has received numerous awards, including the Blaise Pascal Medal and the INRIA Prize. And he was also made a plenary speaker of the ICM and was elected a member of the French Academy of Science. So today he's going to tell us something about PDEs for neural assemblies, models, analysis, and behavior.
Okay, thank you very much. And thank you very much for the opportunity to be again here in Singapore. The purpose of the talk is to convince you, in some sense, that there are many questions in terms of PDEs and stochastic analysis in the field of neuroscience, and to try to convince you to join us to work on this. So the purpose is not to give detailed proof, is to tell you what are the many directions where you can find problems in neuroscience. So the plan of the talk will be this one. I will first tell you how a neuron works, a single neuron. Then I will tell you of three different approaches to describe neural assemblies. So three different types of models, which you will see are all related to integral differential equations. So the discovery, first of all, the topic of this workshop is active matter. So if I understand well, everybody consider active matter as activity is motion. Here we'll speak of activity in terms of electric activity. So it's not motion, it's another kind of activity. Your neurons do not move. So the story began, in fact, at the end of the 19th century, beginning of the 18th century, where they discovered what were neurons. And there is this famous Spanish biologist who described precisely neurons. And from the beginning of the century, they know it is an electric activity. It's like a cable. A neuron is like a cable. You have all along the dendrites and the axons, you have what are called ionic channels, which can open and close, and this let ions come in or come out of the cell, and basically the cell is polarized. There is a difference of millivolts, 70 millivolts, between the internal and external part of the cell. And this is regulated by these ion channels. And Lapik already knew it. A complete description was proposed by Huxley, who wrote this kind of equation. So I wrote it small in gray so that you cannot read it, because it's so complicated that if I begin with this, you say, okay, I will never go in this field. So don't read it. But that is what they did to fit perfectly the experiments they were doing. And because of that, they won a Nobel Prize in 1963. So this is Huxley model. Huxley model is too complicated. Feitzug Nagumo and Maurice Lécart later came with a simpler version of it, what I will use mostly. However, all these models that you take Huxley, Maurice Lécart, Feitzug Nagumo, and all the models that you find now, which are adapted to each type of cells. Neurons are very different. Electrically active cells can be very different. Your heart has also many electrically active cells, which are very different from neurons. So all of them have equations which are adapted to to the precise behavior they have, but all of them, they do the same thing, which means they describe a slow dynamics followed by a spike, which is a fast dynamics, and then going back to a steady state. So here you have Hodgkin-Huxley, here you have another one which is called Fizugnagumo, and you get this kind, always the same behavior, which is called an excitable system. An excitable system means that basically your system wants to go to an equilibrium, but if you push it a little bit by just a small current, then you go to this long spike, this long excursion, and then you go back to the equilibrium. So it's a 2x2 system, dynamical system, which do that. If you look at what is called the Maurice-Lécart system, then it is much more clear. What it describes is the potential, the action potential, the transmembrane potential, the potential difference of potential between the external media and the cell plasma. So this potential is driven by simply the opening and closing of these ion channels. So this GI of T describes the opening and closing of these channels. I equal 1 to capital I describe all this calcium, potassium, chlorine, whatever the ions you want to consider. And they more or less all describe the relaxation of V to one of these given potentials, which are measured experimentally. There is always an external current. This is important because this is the way you couple neurons. So a single equation, this is a single equation for a single neuron. If you want to couple them, you say that each time you have a spike, you create a current that you send to the connected neurons. So this is the way you connect them. And the gating is just described by this parameter. You have an equilibrium depending on the potential, and then you relax to the potential. And because all these gates will open and close at the different times, this will change, and then you are never really at equilibrium. So this is what you observe. Again, if you follow this, you just describe these spikes. So this is a potential, this is a gating variable, or a control. This is a gating variable and the potential. If you have no current, you go to an equilibrium. Your neuron will stop working. If you put a current, whenever you're at equilibrium, you push the system out of its equilibrium, you create this excursion, this excitation, and the current will push you again to a new excursion. And this is, Ethan was speaking about Kuramoto last week. The reason why Kuramoto is used for this equation is that if you have a periodic motion like that with a current, you can use a model on the sphere, which is turning, and you simplify this picture. Kuramoto is a way to simplify this picture here, where you forget now about the physiology of the neuron. The mathematics which is behind, but of course you are speaking of differential equations. Nevertheless, there are interesting mathematical questions. One of them are surface dynamics, which means that the gating variables are not always at the same speed. Some of them are faster than the others, and usually the model is taken by the fact that you have an inhibitory channel, and this inhibitory channel is usually fast and is taken at equilibrium, while the excitatory channel is driven by the gating variable. Okay, so this is an example of question. How do you relax? How do you relax Ti going to 0 in this kind of equations? In that case, it's monostable, it's simple, but there are many problems like that where you have multi-stability and the answer is not so simple. So if you want to describe precisely now a network, the problem is you have to solve these equations with all these channels and couple them. And a small network of neurons, if you take a small piece of your brain, will be thousands, millions of neurons. We have more or less 10 to the power 12 neurons in our brain. So if you want to do that, it's impossible. So physicists proposed to simplify, and rather than following the precise dynamics of each spike, to simplify the model and saying that you have a slow dynamics, which you know by one of these channels, which is the slow dynamics here. And when you reach a certain threshold, then you don't describe the spike. You don't compute the spike, which is very thin, that you need to have a small time step to compute. What you say that you go back directly to the hyperpolarized state, which is here. So rather than describing the spike, you say, okay, describe the slope, and when I reach a certain potential, I go back to this point. So you create a discontinuity at certain times that you don't control. These are the times where you reach the potential, and then you create that, and you say, okay, at this point, I don't know what happened, but there is a spike. And the spike will send an information to the neurons. Okay? So what biologists in neuroscience think is your brain only works by the rate of spiking of your neurons. Whatever you do is transformed in your brain in the rates of spiking neurons and connections between neurons. Okay? So this is the way everything works. So this simplification, you see, is good because now you have a single equation, and this single equation is able to describe a periodic motion, which is not possible. If you take a single differential equation, you go to an equilibrium. You cannot get periodic solution. With these discontinuities, you can do it. Okay, so this is a single neuron. Now, let's go to networks. So networks, you have many ways to see assemblies of neurons. So the oldest one is called neural fields or rate equations, and basically they don't use the precise physiology of neurons. So they go back to several people. I usually quote Wilson Cowan in '72. There are other names behind that. And in that case, you don't want to describe the precise neuron. You precise an assembly of neuron. You say these neurons are spiking with a certain rate n of t. I call n of t the activity of this network. And the only thing you do is to describe, so at each location of your brain, so you take a certain number of part of your brains, or you try to measure everything in the brain. This is what people try to do now. And you measure, and you look at the evolution, the dynamics of this rate n of tx. At each x, you have a rate. And then what you say is that these rates want to relax to zero, but with a certain connectivity, which are the synaptic weight or the connectivity matrix, you are connected to the other locations, and from that you create plus a source term, because you hear me, though you have an entrance which is the source. So you look at something, you have an entrance which is what your eyes send to your brain. So you have a source, you have this activity coming from all the other part of the brain. You create a signal, and and you process the signal with a sigmoid. So this is a function which is 0 or 1, a very stiff function. If the signal is too small, you put it to 0. If the signal is big, you take it 1, and you send it to the new neuron. Okay? So this is the first model invented in the 70s to describe neural activity. Of course, this has nothing to do with neurons. You can see that for any network. If you think of internet, this is exactly what happens. If many people are interested in a video, then everybody will receive the signal and will look at the same video. It's exactly the same kind of model will do the job. So it's not physiologically based. Nevertheless, it is so simple that it is very much used in practice. So it is used for, okay, so what is the mathematics in this? So you have a differential equation what is very interesting is that very quickly when you take weights which are not too simple, you understand that there are many, many steady states. And this is good, because you don't want as a steady state 0, because of course everything is 0, sigma will be 0, n equals 0 is a steady state. You don't want to see this steady state. I mean, if your activity of your brain is at 0, it means that you are dead. It doesn't mean that you are, when you are sleeping, your brain has an activity. Okay? So what is very good in this model, that the reason why it is used, is that it gives you that whatever you do, there is an activity. And not only that, but you can classify the activity, and this was done by many people, and you can relate that to the activity people describe. And in particular, under drugs, people describe always the same image, which is the steady state you get when you change the weight according to the drug you have taken. Okay, so these are images that maybe you have seen. Some of you, I don't know. No, nobody. Okay, so this is. So there has been a lot of activity about that. What you see very quickly, even with a very small network, is that you can generate activity. So this model is already used to explain some neurodegenerative disease, and have been measured precisely in terms of activity. Especially, I have seen a paper on Parkinson, but the same thing is done for many other diseases. Where simply the disease just eats two parts of the brain, two organs of the brain. You know, your brain is made of many, many different organs. And simply, these organs are connected by these synaptic weights. And the change in the weights will change the way the communication of these organs. And very quickly, when you take only two equations of Wilson-Cohen, you don't need a continuous model, you need only two. You see that in certain circumstances, it creates a periodic activity. Okay? And so this depends of the weights. One of them has to be excitatory, the other one has to be inhibitory. It is known that two excitatory components will never generate activity. You need at least one inhibitory component, and this is what you see here. And so if you change the weight, the frequency of dissociations will change, and this is typical of Parkinson disease. So this is what you can do with this kind of model like Wilson-Cohen. There is another, by the way, another question which I didn't mention, but which is connected to that, is how instabilities occur in such systems. Because of course, such a system also have equilibrium which are steady state, and so you are interested in to describe the transition from one state to other one. So bifurcation analysis is very much used in this model to classify the solutions and to understand the transition. So recently, from the end of the 80s, in the 90s, physicists came with another point of view better describe neural net. But I forgot to tell you something important, by the way. If you look at your visual cortex is made of different layers, which are called V1, V2, V3, etc. And so, in some sense, in each of the layer, you have a connectivity within the layer, which is sent to the next layer, where you manipulate this and the same layer. And this is exactly what are called nowadays deep neural network. The deep neural network come from these things in the 70s, exactly based on your visual cortex. So integrate and fire, to go back on that, so this is different. Integrate and fire, you want to describe the real physiology of neurons and to write equations which describe precisely how physically neuron works. So you have many neurons, they're connected, they have interaction, so you want to make a mean field limit and describe the mean field limit of a system of active, electrically active cells. How do you do that? So the usual concept is to what is called the noisy and leaky integrate and fire. Noisy means that when you consider large assemblies of neurons, there is always noise, because there are always connections with the rest of the world, which makes an external noise, or also there are all these dendrites of connections in between them that you don't take into account and create another noise, an internal noise. So you have always a noise, and you have the integrate and fire. So I told you integrate and fire, you follow the slow dynamics that you know, which is easy to compute. You don't compute the spikes, and you have an external current, I of t. So what I wrote here is simply this equation plus the noise. And in the integrate and fire technology, what you say, when you reach a certain potential, the reset potential, the firing potential, you reset it to another potential. You introduce discontinuities from V firing to V reset. Of course, V reset is smaller than V firing. This is the picture we had earlier. So this is much simpler than these models we have seen. That's what we said. Now you can try to understand an assembly of neurons like that. What does it do? So, of course, the first thing you begin to do is use Ito calculus. Okay, first of all, what you see out of it. Now, this is a numerical simulation. What you see is this slow dynamics with randomness. You reach the potential which is fixed to 1. You have these spikes that I put artificially, which do not exist. I have put that artificially in the in the drawing. And then you go back to a reset potential. You have the slow dynamics. You fire, and so on. Okay? So this is now what you see if you follow a trajectory like that. So this you don't see, it is artificial. Again, this I did it artificially. All this has been very, very much studied in details by physicists. And in particular, what they did is to try to find what is the best description of the slow dynamics you can do to fit experiments. And this is the kind of picture they produce. You have an input current, you have a neuron working like that, and what you observe with different function h are different output. And they came out that the exponential weight, okay, there are formulas for the best formula, which the best function h, which is a reset, which is a leaky, which term which converges to an equilibrium plus an exponential term for describing the spikes. And so this has been done very precisely, and they know exactly for each neuron what is the correct description. Okay, So now if you want to understand what happens with such a system, you use Ito calculation, you write the probability law to find the neuron at a potential V. So now you don't have particles, you have a distribution of particles. You look at the probability to find a particle at a potential V. So I'm sorry, usually PDEs, the name of the variable is X, the name of the unknown is V. In the field of neuroscience, the variable is V, and the probability is N or P, depending. So I'm sorry about that, but this is the habit on this field. So the distribution of potential V is driven by the drift, H of V plus a current, a noise, which is a Brownian motion. And now you have to write that you reset neurons at a potential V reset. So this means that you have a source, which is a Dirac mass at the potential VR, with a certain weight, which is the total number of neurons that you reset. And this, how do you compute that? You compute that because your potential is always at VF, because when you write in VF, in any case, you reset at VR, which is smaller than VS. So your equation is set on the half line V less than VF. At VF, you have no neurons, because whenever they arrive at the potential VF, you remove them to put them here. And the activity is simply the flux of neurons arriving at VF. So this flux of neurons arriving at VF is reset here. And if you integrate, because of the Dirichlet boundary condition, if you integrated V, this term, you see that this term will disappear because of the boundary condition. This one, when you integrate, will give you the N of T, which exactly compensates this term. So in some sense, you describe a probability density because of this. Okay, you can see also N of T as a multiplier you need to get a probability measure for all times. Okay, so this is the integrate and fire. So it's some sense very simple. It's just a drift diffusion equation in which you create a source to compensate the fact that you are working on the half line. So this is still the description of a single neuron. But now I've written simply a probabilistic description of a single neuron. They are not connected. Okay. So just to tell you what this equation is doing, it's a parabolic equation with a drift. It's more or less like the Fokker-Planck equation. What you expect, and it's what we proved with José Carrillo and Maria Cáceres, is that if you don't put an input current, if the input current is zero, then the solutions exist, they are smooth, and they converge to a steady state. And this is simply the desynchronization of a system of particles. You have a system of particles, each of them moving randomly. What you get is simply their probability distribution, the stationary distribution, P of V. That is not very surprising. What is always more interesting in this kind of questions is to prove that you converge exponentially to the steady state. The steady state, by the way, is here. It looks like a Gaussian, except that you have a kink because of the Dirac mass, and you have the zero boundary condition here. So the proof of the exponential convergence is based on relative entropy. For all equations like that, you have a relative entropy. The relative entropy is written like that. P of V is a steady state. So for any convex function H, this quantity will decay, and it decays for two reasons. One is a diffusion, the other one is a jump. Okay, so the diffusion term is here, and you have a Poincaré inequality, which tells you that the entropy itself is controlled by the entropy dissipation, which is this one, whenever you have subtracting the steady state, so when you have this mass 0. So this is the usual Poincare inequality in a half line. But basically, the proof of this with a zero boundary condition is not so old. It goes back to the beginning of this century. It has to do with all this activity about log-Sobolev inequalities and all this functional analysis which is going around this. So now let's come to your question, Russ. How do you create networks? So now the rule is very simple. You have a current. The current is proportional to the activity. So we said that we have an activity n of t, which you compute from the boundary condition. And that you say that this activity creates a current. And this current is a connectivity parameter B multiplied by the connectivity parameter B multiplied by the activity n of t. Okay? So it creates a nonlinear drift. And of course, you see that now it becomes a little bit tricky because the drift depends on the boundary condition. And of course, the boundary condition, the flux of boundary condition, depends on the drift. And so this becomes a little bit tricky as a nonlinearity. And this is all the difficulty. In the literature of physics, you will see that the noise is proportional to the activity also. What I will take here is always that the noise is fixed. So A of n of t 0. By the way, you even don't know if you can solve this. If the noise is proportional to n of t, you even don't know if you can define n of t by that. So it's one of the difficulties. So I will take A constant. So now you see that you can describe what is when is an excitatory and an inhibitory network. When B is positive, the current increases more. This is an excitatory connection. If B is negative, you have an inhibitory connection. Okay. So this is the way you do it. So you see it's simply a nonlinear PDE where the drift is nonlinear, depending only on time, constant. So that simplifies things, but depending on the boundary condition. And this is a difficulty. So what can we say about this equation? Okay, first of all, how do you establish such an equation? And this has been done by a number of people in probability. So for some reason, most of them are French. There have been a huge interest in the French community about that. And simply what they do is you write the system for a number of neurons, capital J. Each of them is connected to the other ones by this current. This current is simply at each spike you create a small current because you divide by your coefficient J here, and you have the connectivity B here, beta here, which is connected to B. So at each spike you create a current. Okay. So this is the interaction between cells, which is here between spikes. And if you, and all this community have been proving that when capital J tends to infinity with independent Brownian motions, then you converge to this equation. So the mean field limit of this system, of this particle system, has a limit, which is this nonlinear equation. Okay. So you can it's not easy to prove because it's not at all like particles interacting with binary interactions when they are located at the same place, or even in these flocking problems where you count the number of individuals. It's much more tricky. It's really each neuron follows his dynamics. It reaches the firing potential at some point and then sends the signal to everybody else. So it's really a mean field limit, but in a very tricky way. So the outcome is this. So what do we know about this equation? So the first thing we could prove is that if you give me an initial data probability measure, smooth enough, when B is small enough, which means that it's not too much excitatory, depending on the initial data, then you have a solution. If B is negative, which means that you have an inhibitory network, then not only you have global solutions, but they are globally bounded. And what we know, if B is small, then you are close to equilibrium. B equals 0 is a linear case where you know exponential convergence. If B is small enough, it converges to a steady state with an exponential rate. And this is what I would call perturbation theory. You have a Poincaré inequality. Poincaré inequality gives you the room to put a small nonlinearity, but a small nonlinearity only. So they are full of open questions in this field. With a major one is to prove convergence for the inhibitory networks. For inhibitory networks, we believe that there is a unique steady state. We believe that it is asymptotically stable. It is not proved. There is a way to reduce this problem to a Stefan problem in some cases, which give you the answer. What we know, which is also very counterintuitive, is that if you put a delay in the response, here I said that your current is directly at the same time the activity. Usually you say that the connection takes some time, so you put a delay in the answer. If you put an inhibitory network with delay, you can create activity. So the delay which seems to be a simply regularizing effect, can create a synchronization of the network. But for an inhibitory network, the difficulty to prove anything for large-time convergence is there is no notion of entropy, of energy, or whatever. These are not closed systems. In some sense, the neurons, they create these spikes, but they have as much energy as they want to create the spikes. There is no, the energy is not considered here. So this is just to show you what happens for an inhibitory network. So you get this dynamics, which looks like a Gaussian. You create, of course, a kink, and this will stabilize nicely with time. So this is an inhibitory network. We believe that this computation is telling you the truth. We don't know. What was most surprised, because this problem really come from physics, is what we proved with José and Maria, is that if you are not in the condition of the theorem for existence, there is blow-up. So typically, if you give me an initial data, is B is too big, or if the initial data is too concentrated close to VF, to the firing potential, then the solutions will blow up. This means that there will be no smooth global solution. And what is more surprising is that the proof even tells you that it is even worse when the noise is bigger. So if you have no noise, by the way, it will not blow up. You need the noise to make it blow up. And the values of B doesn't count. It depends, it's related to this initial data. Okay? So the system typically blows up. So when we proved that, I was very happy. And I said, okay, I will go to, I went to see my friends in physics. and tell them, okay, your models, because these people are from my generation who did that, your model is stupid. It doesn't, it blows up. There is no solution. And so they said, you didn't understand what happens. What happens is simply that what you consider as a blow-up is not at all a blow-up. It's simply the synchronization of the network. At some time, the network synchronized, or is partially synchronized, and this is what you see in all these models of Kuramoto style, except in Kuramoto, you don't see it as a blow-up. Here, it is really the same phenomena, which is the synchronization of the network, and which you see here. So, what you observe of the phenomena of blow-up is, at the beginning, everything is like as before. You create a kink, but the difficulty is that the slope here, which gives you the activity, is still increasing. And you see that at some point, the network cannot sustain the boundary condition. You cannot sustain that the Dirichlet boundary condition is true, is satisfied, simply because a number of neurons arrive together at VF. So rather than being a smooth solution, then suddenly you create this infinite slope on the boundary with this jump of the density at 0. Okay? So let's see it again. So this is what you will see here. So you see here that you cannot, the boundary condition, which is enforced in a weak way in the numerical scheme, cannot be satisfied. So what we did is to include in the model some regularizing effect. So what we said is that the firing potential is random. So you don't fire at 1, you fire with a certain rate when you exceed 1. So we take this rule to fire. And what you see is, in that case, is that now you have smooth solutions, globally smooth solutions. They create the kink slowly here. Here you create this kink. You go above 1 because your model allows it. It wants to create a large discontinuity, but of course it's smooth, so it doesn't create it, and you create a periodic motion. So when you regularize the system, what you create is a periodic solution where you have synchronized the neurons. And of course, there is no proof of anything like that available. But that's what you see. And though the dynamics then becomes completely periodic. There is a recent paper by these people, Delarue, Natoshi, and Snolkikov, for different models, more closer to the Stefan problem, where they prove that after the singularity, you can continue in more or less a unique way the dynamics. So it seems to be the same here, that if you regularize the model, there will be a unique limit after the blow-up time. No, so very quickly, I just say a question with connectivity. So you can with conductances, you can keep the ion channels in this kind of equations. If you keep the ion channels, simply you include the gating variable that I showed in the Maurice Lécart. For some applications, it is very useful, and you get this equation, which was written in the time when Courant Institute were one of the leaders in neuroscience, 10 or 15 years ago. Everything was coming out of Courant Institute, and this is what they were producing. So they said you get these equations, which is, if you want, in terms of kinetic theory, you can see the voltage equation as the macroscopic state, and this as the kinetic Fokker-Planck equation. You have noise on the variable g, you have a drift, and here you have the usual term that we have encountered. Okay? So in some sense, here you have a kinetic view. You expect that if this gamma means this parameter, what you call gamma for Fokker-Planck is big, you get in the limit the Fokker-Planck equation. So in some sense, you should be able to redo all the theory of convergence of kinetic theory in this case. We did a little bit of it with Delphine Salors, Jenan Zhu, and a student, Xian Du. We studied that. We know that the solutions are globally bounded. We know that the solutions are also bounded in LP. There is no blow-up. We know we have a theory for asymptotic theory to get the macroscopic state from the microscopic state. And there are many open questions. This we did not really understood all the details. Let me just mention that all this question of hypocoercivity, which we have 10 proof of hypercoercivity for the kinetic Fokker-Planck, none of them work if you want to work in this equation. So nobody knows how you can prove long-time convergence with this exponential rate. Here. This is an hypoelliptic operator. You expect that the solutions are bounded, not only bounded, are smooth. The problem is you have boundary conditions. I didn't write the boundary conditions, but these are boundary conditions. And nobody knows how to handle the boundary, and these are how to handle hypocoercivity for hypoellipticity for this boundary condition. So it's an open problem. That's the reason why you have L infinity, but we don't have more. Okay, so all this is interesting. For those who like Keller-Segal, you have the same contradiction than in Keller-Segal. In Keller-Segal, the macroscopic equation blows up, the kinetic equation doesn't blow up. Here it's the same. The macroscopic Fokker-Planck equation blows up, the kinetic Fokker-Planck equation doesn't blow up. Let me very quickly speak of the third type of model for neural assemblies, which are the elapsed time models. So in the elapsed time model, what we want to do is different. You don't want to describe the voltage, you just describe the rate of spiking. So after each spike, you record the time elapsed after the spike. So what you write is that the time after the spike evolves like the chronological time t. So you have a single transport equation, dtn plus dsn, the real equation, and with a certain rate, depending on how the time you have been waiting, and depending on the network activity, you will spike. So this is the firing neurons. When a neuron spikes, what happens? You are again at s equals 0. You have been spiking, so your new time is 0. So you have a boundary condition at s equals 0, which tells you how many neurons have been spiking. This is n of t. So the activity of the network now is defined by the number of spiky neurons, which is exactly this number. Okay? So this is something very close to what is called the renewal process, which I remember in the case of epidemic was introduced by Kermack and McKendrick. So Kermack-McKendrick in 1917 not only write the SI model for epidemiology, but from the very beginning they said the SI model is not enough to describe an epidemic spread. You need a renewal process, and they wrote this equation not with this nonlinearity, with a different nonlinearity for epidemics. So this goes back to 1917, and this is the adaptation of it for neurons. Again, you say that if R is increasing with Bn, this is an excitatory network. If the activity decreases the rate of firing, you say that it is an inhibitory network. So same thing, you have the same terminology. In terms of S, the function R of S looks like something like this. What did you say about the pens, Dunia? So it's something like this. Here you have a Bn of t. This is S. This is R of S. So something which is 0 and which is 1, let's say. Because you have a refractory state, you have to wait before you fire again. What we know about that, which is different from the integrate and fire, is that for an excitatory network, if the connectivity is small or large, then you go to a steady state. You have convergence to a steady state. It's not like in the integrate and fire case. So it's only in the middle range that you get periodic oscillations and you get synchronization. So let me skip about that. Okay, this is the method you to prove convergence to steady state. There are many ways to do it. The advantage of the real equation, it is so simple that all methods you know to prove a convergence to steady states, they will work for real equation. And so that's an excellent problem, an excellent equation for your students, because you can test all the method you know, Poincare inequality, Dublin method, a method of semigroups. They all work very well for this equation. I'll show you what you observe. So this is a solution of this stupid equation, dtn plus dsn equals 0. The transport equation with coefficient 1. This is a solution. So you see that it contains a lot of structure, and what you see when B is in the correct range, that you create periodic activity. At some point, you create these periodic solutions. By the way, these are the measurements that you get from developing network in experiments. And so you have always this asymmetry in the dynamics where you have a fast growing spike and then decreasing activity. Okay, I stop here. What I told you that you have 3 ways to describe activity of a neural network and a neural assembly. The first one is a Wilson-Cowan. You say that your input, which coming from the other neurons and from the source, is simply manipulated by a simple rule, 0 and 1, a sigmoid. So this is Wilson-Cowan. If you want to do it for integrate and fire, you have to solve a PDE. You have your input current in the drift. From this drift, you compute the activity n. And so you don't have access directly to n by opposition to this one. You have access only to the distribution of n, which tells you what is n. And if you have an elapsed time model, you create an input from the network, and you create an activity again like that by solving a PDE. There is one more. No, that's a conclusion. And it's good that it's a conclusion because it's finished. So I have tried to convince you that there are many interesting nonlinear PDEs in neuroscience, which are very singular, very nonlinear, very complicated to understand because the nonlinearity comes from the boundary condition. That there are many open questions, and one of them is the emergence of synchronization. And there are many other questions to see. So thank you very much. These are my collaborators for this. Thank you very much.